Hello Professor Garimala, my name is Vinay Murthy and this is the video for the first assignment of data mining. I'm going to shift to the screen now. I have used the bike bias dataset which predicts whether a person is going to buy a bike or no depending on different features. Let me just visualize the dataset. This is the dataset. It has different features like marital status, gender, and I've changed the category variables into dummy variables here. And income, children, education, age, and even for the commute distance over here, I've changed it into dummy variables like 0 to 1 miles is 1, and for 3 is around 10 plus miles, and etc. Sorry, 5 is 10 plus miles, and so on. The best part about using Azure ML Studio is if you just click on a particular column, it gives a brief descriptive statistics which provides us the median salary of this particular data set would be 60,000, and if there are any missing values or no. It also provides a visualization where we can visualize the relationship between two variables to find out correlation. So for male and female, say for example the different income rates. So this is the basic descriptive statistics which it provides just by looking at this, which would help us better understand correlations between two variables and make basic assumptions for our data model. And I've used summarized data as well, which provides like basic descriptive statistics but also more. Like it provides first what all values lie in first quartile, third quartile, and the variance, standard deviations, skewness, kurtosis. Well, if we can see, there's a high number over here, very high. That is the income, that is the continuous variable, which is pretty high compared to all the other values in other features. So and also if we just click on different columns here, it provides the basic statistics of the different columns as well, and also we can compare it with other different statistical features over here in the visualization, which is very strong in terms of statistical analysis if we want to infer or basic, as I told before, make any basic assumptions we want to make. So since the income value is too high, I've decided to normalize it using natural logarithmic function, and I've chosen only income here as it is a continuous variable, and I've summarized the data again. You'll see the results for that once again after normalizing. So after normalizing, as we can see, for income it has pretty scaled down to 0 to 1 for such that the model will be able to better define relationship between this one and the predicted variable, and others all are pretty much same. And this particular summarized data is found in statistical functions with other operations, which is very helpful, like compute telemetry statistics, testing hypothesis, again to make basic assumptions and to get a feel of what the data is. Next, I've used the split data operation, where I've split the data into 80% and 20%. 80% I'll be using for training the model, and the other 20% I'll be using to test the model on score model. I've used the two-class decision forest for making as a model to classify in this particular data for this particular data set. So the two-class decision in the train model, I've chosen the purchase bike numeric as my predictor model, the predicted variable. So in the train model, if we visualize, we get to see a bunch of decision trees. I'll pause it. Okay, good. Now the statistics has loaded. So this is the basic decision tree which it has thrown our model, and these are different variables which the decision tree has chosen. These nodes have been chosen based on ID3 algorithm. That is, the lowest entropy value will be chosen first, which provides more information to our model. So if we just see, like, this is the trained prediction of not buying a bike, what would be the scenario for that? Cars are, so different features would be commuter distance is 5 to 10 miles, has one car, not married, has 3 children and has a very low income would probably not buy a bike. That makes sense. That's good relationship between income and prediction. And also, if I have a car and 3 children and have earned pretty less, I wouldn't be buying a bike. So the same thing, if I want to choose for one, if I will buy a bike, if a person does buy a bike, the commute distance is again 5 to 10 miles, no children, has 3 cars, but the income over here, as we can see, is pretty high compared to what we saw earlier. So we can conclude, we can make a basic assumption at least, that income has a huge influence on the prediction here. That's for the training, and that's how different trees have been created. And now to score the model, so here I've used 20% of my data set to test our model, and in this the main criteria would be these two columns. So this is the scored probability, that is the predicted labels, this is the actual labels versus the predicted labels, and these, as we can see, anything more than 0.5 has been predicted as 1, and anything more than below 0.5 has been predicted 0, and anything which is 0.5 is also predicted 0. That means the probability of someone buying, if it is 12.125 of the data set, is classified as 0, and anyone more than 0.5 probability of buying a bike, depending on different features like age, marital status, children, commuting distance, cars, would be 1, classified as 1. And the next thing I would go is to evaluate the model. So to visualize the results, this is the curve which we have, which is a ROC curve for true and false positives. Looks like a fine curve, not bending too much towards false positive rate until here. And to get a better judge of it, we can look at the confusion matrix here, true positive and false positive, that is of how many people will actually buy the bike versus the predicted that it predicted right that they're actually gonna buy the bike, and false negative is how many people who are actually buying the bike and the model predicted that they will not be buying the bike, and the ratio between these both will give the misclassification rate. And the same goes for false positive and true negatives. True negatives is whoever will not buy the bike and actually the model predicted they won't, and here the model predicted that they will, instead it should have predicted it won't. The accuracy is 62.5%. The threshold, as I told, 0.5, I have kept it at 0.5 because as anything above 0.5 would be classified as 1, below would be classified 0. These are different bins in which data points lie, and what are the accuracy for different in that particular bin. That is 56% accuracy of our prediction. Yeah, I think that's about it for this particular video. Thank you for listening.